Thank you. Okay, what we're going to cover today is obviously definitions of a systematic review and a meta-analysis. We're going to talk about how you collect data for these kinds of things. And that is definitely not as straightforward as you might think and is totally critical. How you're going to organize your data for the meta-analysis, how to run the meta-analysis and interpret the results, how to make some useful graphs. We're going to discuss a few things that might compromise the results of your meta-analysis. Lots of resources for further information. And all of my examples in this workshop are going to use continuous data. No binary data are used in this. And that is simply because especially when I get to my PowerPoint slide deck, you will immediately see that I have way more information than I can cover in the allotted time. And I'll go over which parts of this I'm actually going to have to skip. But the only reason I left out the examples using the binary data is I just ran out of time. We are not going to use this as an introduction to the use of Stata software. So if Stata isn't something that you're comfortable using, then you'll still get a lot out of this workshop, but the code might seem a bit mysterious to you. We're not going to be discussing how to access and or use the electronic databases that are typically a major source of information for the meta-analysis. And we're not going to cover any of the more advanced topics, such as meta-regression, which isn't all that advanced, but we're still not going to get to it. Multiple imputation, Bayesian, multi-level, we're just not going to get to those things today. The example data are here in this file here, and the PowerPoint presentation is right here. Looks like it didn't have a carriage return in there, but those are the two links there. The data are totally faked. I mean, completely and utterly faked. I literally just sat here and made up the data. And I did that in part because I wanted to put some features into this to show you what would happen if you found these in the data set that you're actually working with. So I had to build a little bit of that stuff into my data set here. So here's the PowerPoint thing. This is the introduction to meta-analysis in Stata. We went over what to expect and what not to expect, so we're good there. Yes, there are 181 slides, which is why I said there's too much to cover in the 3 hours, but there are some blank slides in there like this when I have a section break, and then there's reference slides and stuff. And then the output takes up a whole bunch of slides, so don't panic at seeing that many slides. I'm going to skip the parts on quality checklists, a lot of the math regarding the heterogeneity measures, and the very end, the cumulative meta-analyses, just because I got to skip something. But all the information regarding those topics are in the PowerPoint slides and in the web page. So you still have complete access to all that information. I'm just not going to go over that during this presentation. Because all I see is my PowerPoint thing, I can't see if you're putting information or questions into the chat. I'm going to let Andy and Katrina take care of the chat, but if you'd like to ask me a question, please just unmute yourself and ask. It's always nice to hear from folks because, like I said, I'm just sitting here talking to my monitor and it's kind of weird. So if you like to let me know that you're still there and listening, that's wonderful. We will have a couple of breaks, but they'll probably be kind of short because, like I said, got an awful lot here. So let's get into it. Here's the introduction. Okay, so let's imagine this scenario. You're listening to, I don't know, the radio, TV, YouTube, whatever it is you listen to get news and information. And you hear about a new drug, a new treatment, diet plan, whatever it is you hear about, and it sounds great. And there's this quote from the author that this research needs to be replicated with more subjects before anyone should act on these results. And you think, yeah, okay, we always hear that. So you go out and you do a little bit of research, and you find that there are a number of studies that have looked at whatever it is that you heard about, and you find that some of these studies replicated the results while others did not. And as you're thinking about it, you notice something kind of odd. You notice that when there are more participants in the study, it's more likely that the study was to find some sort of statistically significant result, maybe that the diet plan worked or the drug worked, whatever. And so you think to yourself, well, that's kind of weird. Why would my treatment plan be more effective if there are more participants in the research? That's just weird. And so what you have said to a statistician, what you've said to me, is that you're not actually interested in the number of participants or even whether the result is statistically significant. Rather, what you're really interested in is the effect size. And we'll go over what the definition of that is in a minute, but that's what you're interested in. And from a statistical point of view, we know that as n goes up, the p-value goes down, holding everything else constant, everything else being something like alpha and the effect size. One other thing, I am constantly told that there are too many words on my slides, and I'm just going to apologize for that now. There's lots of words on my slides. Do not feel compelled to read my slides at this time. You can just listen to me ramble on. That's fine. All those words are there mostly for me so that I don't forget something. And for you, when you come back to this and you're thinking, gee, she spoke about something like this and I don't remember the details, there are complete sentences, there's full ideas, and you can actually pick up what it was that we were talking about when you come back to look at this. So I hope that is helpful to you. All right. So as we said, adding more participants to a study should not make the treatment more or less effective. You know, that those two things should not be related. But what you really want to know is, does this treatment, diet plan, whatever, work in the real world? Now, according to Wikipedia, in statistics, an effect size is a quantitative measure of a magnitude of a phenomenon. And that's as reasonable a definition as I have seen for effect size. It's a number, a quantitative measure of the magnitude of an effect. And there's lots of different kinds of effect sizes, and we will go over some of those today. But what you're really thinking to yourself is, okay, I'm interested in the size of this effect, not whether or not it's statistically significant, because statistical significance, for the most part, is driven by n, the number of participants, and that's not what you care about. You want to know, is this effect size, say, small, medium, or large? And that's a reasonable question. All righty. So collecting information from studies, hopefully many studies, that try to answer approximately the same question is kind of like doing your own meta-analysis. That's really what we're going for. We're looking for effect sizes from the literature, usually the published literature, and we're gathering all those up. So we need not only the effect sizes, but we need estimates of their error, because an effect size is like anything else we estimate in statistics. We never estimate it perfectly. You know, we're not that good. We have an estimate of its error. And whether that comes in the form of a standard error or a confidence interval, either way is okay. But you need to have those things. You want to be looking for studies that have what we call an apples to apples comparison. So you want the studies to be addressing very similar, if not exactly the same research question. And in some areas, that's fairly easy to do. And in other areas of research, especially in social science research, that's a little more difficult to do. But you do want them doing kind of the same thing. You want the same kinds of measures to be used, the same kind of outcome measure or the same kind of manipulations, whatever's going on. You want it to be similar across the studies that you're going to include into your meta-analysis. But other things don't have to be similar. You know, the number of participants, I don't care if it's small or large, really. What you do care about, though, is that in whatever write-up you find, that you do have this effect size or some numbers that you can use to calculate the effect size. So in my example, I don't find the actual effect size. I find numbers that allow me to calculate that, and hence its standard error. All right, what else do we have here? A systematic review is very, very similar to a meta-analysis, except for the effect sizes and possibly other values aren't collected from the articles. And so there's no statistical analysis here. But a systematic review is one of those kinds of things that you almost have to do in the process of doing the meta-analysis. All right, we need to discuss 4 related quantities here. All right, alpha. Most folks are familiar with alpha, and it's the alpha that everybody's familiar with. It's the probability of rejecting the null hypothesis when it is true, and that is usually set to 0.05. We have power. Power is a probability. It's a conditional probability of detecting an effect, given that that effect really does exist in the real world. Now, power can either be something that you go looking for, you know, when you're conducting an a priori power analysis, or it can be observed after the data are collected. But either way, we're talking about power. An effect size, again, the quantitative measure of a magnitude of some phenomenon that exists in the real world. It can be estimated, such as when you're doing your power analysis before you've conducted your research, or it can be observed, which means you figure it out after the data have been collected. What I always suggest to people is that after you've run your study, go calculate your effect size and see how good your guess was beforehand, right? You had to kind of guess at it when you were doing the power analysis before you collected your data. Afterwards, see how accurate you were, and maybe that'll help for the next power analysis you have to do. And then we have N, which is the number of subjects, participants, observations, whatever you want to call it, who participated in a primary research study or are needed for such a study. Okay, so those things all work together in any form of research. So let's have a few examples. If I hold alpha and the effect size constant, as N goes up, power will also go up, right? So that makes sense. The larger my sample size, the greater the power, right? If I hold alpha and power constant, as the effect size goes up, the number of necessary participants goes down, right? The larger the effect size, the fewer folks you need in order to detect that effect size. If you hold alpha and N constant, as the effect size increases, power also goes up. And of course, so does the probability of finding a statistically significant effect. I don't want to focus a whole bunch on statistical significance in this workshop here, but it's a related concept, which is why it comes up. All right, very quickly, any questions before we move on to guidelines? All righty, I hear only my cats in the background and they don't have any interesting questions. So I'm going to guess that there are no questions at this point, and we're going to move on to guidelines.
I actually have a question.
Yes.
So I don't know if you're going to be talking about this within this PowerPoint or lecture, but I was wondering about the use of covidence for the facilitation of basically completing at least the review, the systematic review portion of the meta-analysis. And if there was any information within the UCLA system, either within your department or the library, on how to use that software.
Use what software?
It's called Covidence, and it's basically a systematic review software that you link it to like EndNote or another database that you're using, and it will kind of automatically do the systematic review for you, as well as the data quality or the data quality assessment piece as well.
I haven't heard of it, which definitely means I'm not going to be talking about it. If you're affiliated with UCLA, I would suggest that you come to our remote consulting, and Andy can give you information about that via the chat, and we can talk about it.
Okay, thank you.
Okay, so guidelines. There are guidelines that, for the most part, you need to follow when doing either a systematic review or a meta-analysis. And I'm spending some time here to introduce these to you because at this point, trying to get anything published without having used at least one of these guidelines is very unlikely. You've got to follow one of these guidelines, and they have very, very specific requirements as to what you need to include in your write-up. And I want you to be aware of that because you need to collect information as you move through each step. And the very last thing in the world you want to do is have to go back and try and recreate the steps that you've already gone through. So if you know what you need to collect as you're going through it, you'll be collecting the information you need, and that will make your write-up a whole lot easier. So the idea here, though, behind the guidelines is that it's all about planning. Okay, all good research, whether it's a meta-analysis or anything else, is all about excellent planning. And so these guidelines are here as a way to kind of help you with this planning, because although meta-analysis is in some ways like other types of research, in many ways it is very different. And if you're new to meta-analysis, you might not know all of these different things that you need to be paying attention to. And so those guidelines are here to try and help you say, hey, you got to pay attention to this. Hey, you got to collect this information, and to help you along your way. Please read these guidelines before you start doing anything else. All right. You will save yourself a lot of time and a lot of frustration if you do. And I'm going to go over what they are right here. So, like I said, there's a number of them. I've never encountered a reviewer or anybody else who has been particular about which set of guidelines you follow, and they're all very, very similar. So it's not like you're going to get really different advice if you follow Moose versus Strobe or Prisma or anything else like that. They're kind of geared towards slightly different fields of research, but again, they're all terribly similar. So have a look at whichever of these best fits what you are looking at. There are two organizations that do lots of research and publish a lot of meta-analyses. We're going to go over those in just a second here. Both the Cochrane and the Campbell collaboration help to set the standards for good meta-analyses. All right, so when you're looking through things, if you keep coming across something that talks about the guidelines from the Cochrane collaboration or the Campbell collaboration, that's exactly where you want to be, what you want to be looking at. I will warn you, though, that both of these groups are extremely active. And so their guidelines get updated, I would say probably at least once a year, if not more frequently. So just because you published a meta-analysis a couple of years ago, you still will do yourself a good favor by going back and reviewing what the latest and greatest is in these areas as you start to work on your new project. Okay, those things get updated frequently. Cochrane Collaboration, it's an organization that collects data mostly in the medicine and healthcare kinds of fields here. They tend to have international clients, so they do lots of meta-analyses. The guidelines actually look like a book when you look at it online. Don't let that intimidate you. It's all very readable. It's all very doable. You know, there's like a handy dandy checklist. So don't panic at the amount of information. There are nice summaries that you can go to. The Campbell Collaboration was founded in 1999 and it is actually named after Donald T. Campbell. If you're in the social sciences, especially in psych, that name will sound familiar to you. Yes, it is the Cook and Campbell, that Campbell there. They look at social issues here, and but they also link to the Cochrane Collaboration Guidelines as well as other guidelines. And so there's all sorts of great stuff here. So anyhow, be familiar with these things. That will save you a lot. They're all very similar. Reading them will help you understand what you need to have ready when you go to do your write-up. This is the section on the quality checklists. The idea here, and I'm going to skip over all of this because I have to get moving or I'm not going to finish on time. But the idea behind the quality checklist thing is that it is true that not all research is of the same quality. And you may want to assess the quality of the articles that get included into your meta-analysis to ensure that, say, some piece of research that may not have been of terribly high quality is having some sort of undue influence on your results. There's all sorts of issues with quality checklists. There's like thousands of them. I mean, I'm not kidding. I mean, like literally there's like thousands of those things out there. Very few of them are validated measures. And that got to be a real problem because it turns out that if you use different quality checklists, you could get very different evaluations of your different studies, and that didn't make anybody feel so good. So anyhow, all of my information on quality checklists and stuff is in here. You can go ahead and have a look at that. So let's start talking about how you're going to collect your data. You're ready to start your data collection process. And the first step is to state the research question very clearly. Obviously, this is a critical step just because obviously you got to have a good research question so you know what you're doing. But in addition, this question is going to inform the criterion for what studies will be included versus excluded from your meta-analysis. So the research question, I mean, obviously, anytime you're doing research, you want to state your research question clearly, but this is kind of a different level of specificity. And that's what I want to convey here is that it has to be crazy specific because you have to be able to use this to decide what studies get included and what studies do not get included. And it may turn out to be kind of an iterative process of refining this question depending on how many studies you get back when you go to search the databases. So basically what you're going to do is you're going to go out and you're going to say, hey, look, the library has these various electronic databases, they're searchable, and these databases contain published studies that may be relevant to my meta-analysis. So I'm going to go search them, and you need to indicate, well, which ones are you going to search and what search terms are you going to use and stuff like this. And sometimes the terms that you put in yield way too many results. Okay, so I've published a number of meta-analyses. I've got a couple more in process, and they've had times where we've put in the search terms and it came back with, something like 50,000 results. And we all just kind of cringed. Like, we cannot go through 50,000 studies. That's not possible. I can't do that. And other times we've done this and it came back with like 3. I'm like, 3. Can't do much with that. That's not going to work. And so, you go back and you either expand the question or narrow the question so that you get something that you could actually work with. Okay. And that's why I say sometimes it's more of an iterative process than you might think, because, sometimes you just can't work with what came out of your search. There's also a lively discussion regarding the so-called gray literature. Okay, that's different from having gray hair, although sometimes the gray literature can give you gray hair. Ask me about that. No. When you're going through your research, the published literature is usually pretty easy to access because it's in these databases, or at least if it's too recently published, you know about it, you got the journal or whatever else. But there are other kinds of literature that are not so easy to access because either they're not published or they're not published in something that got into one of these databases. So something like that. There's a question as to whether or not these articles have undergone the peer review process, which in some cases is very important and in other cases really isn't as important. These gray literature things could be something like a master's thesis or a dissertation, government reports, NGO reports, researcher reports from businesses, white papers, conference proceedings, statements by professional organizations, etc. And you can, as you look through that list of, and that's not an exhaustive list, but it's a fairly comprehensive list of what the gray literature encompasses. Okay, finding master's theses and dissertations, if I was only looking for stuff within the University of California system, I'd know what to do. I'd know how to do that. Outside of our system, I don't know how I would really go about that, and I don't know how far back they go. But all the rest of this, man, it would be really hit and miss. And so you need to think very carefully about what, if any of this, should be included in your meta-analysis. Again, a lot of that stuff is not peer-reviewed, and so the question of quality, of course, comes up, and you need to ask yourself if the quality is high enough to be in your meta-analysis. One of the questions that we always ask, if it wasn't good enough to be published, why is it good enough to be in my meta-analysis, right? So these are questions that you ask yourself and you decide on a case-by-case basis. Again, very difficult to access a lot of this type of literature, and so you worry very much about well, I found this, but this stuff in reality should have been included, but I wasn't able to find this. And so I worry about, kind of missing pieces here. So again, this access thing can really have some important implications here, because you don't want some sort of selection bias to creep in here. Omitting all of these, which is something that a lot of folks do. I mean, don't get me wrong, a lot of people really shy away from the gray literature because it comes with a lot of issues. On the other hand, some people argue that omitting such information could lead to an inflated estimate of your summary effect size, because some of the effect sizes reported in the gray literature would likely be smaller than those in published articles. So again, there's no super clear answer here, but it is something that you need to think about carefully, because you are going to have to discuss it in your write-up, whether you use gray literature or not, and what motivates your decision. All right, so let's say that we've got all that resolved, and now we've able to search our databases, able to come up with a list of potential articles to include in our meta-analysis. We need to think now about inclusion and or exclusion criteria. So this is kind of the idea of, well, what comes in, what stays out. In practice, what I usually do is have exclusion criteria. And I say, look, everything is in until I have a reason to exclude this. And that exclusion criteria usually it's just a list of things that you go through. And one of the things that you'll have to keep track of is how many articles got knocked out for each of those different criteria that you specify there. So let's see here. Some examples of stuff that I have used in the past. Articles not written in English were excluded because I've never actually worked on a research team that had any member who could read anything other than English. That may be a limitation on our part. I don't know, but that's just been our reality. So we've only used stuff that was published in English. You always want to put on a data publication range here. And you can't say something like, say, 1980 or later, in part because, nobody knows what the actual end would be. If they read your paper 20 years later, it's like, well, it didn't include stuff after we published it, of course. You got to put it, got it bounded on both ends. And remember that the databases are not like up to the moment updated, and they update at different intervals. So you do want to cap it on one side and the other. Again, publication source, we stuck with just peer-reviewed journal articles for most of the stuff that we were working in. But for us, that wasn't a huge limitation given the topics that we were looking at. It didn't seem likely there would be much in the gray literature, if anything at all. So it wasn't like we lost a lot there. But that was just because of the topics that we tended to look at. And I don't want to make a general statement there. At least in the, at least the last two that I've done, we only used experimental designs. And in one case, it couldn't be anything other than an experimental design. But in other cases, in like social research, what we did was we excluded field studies and stuff like that. But this is the kind of thing that you're going to look at. I've seen others where they've put a restriction on the age of the participants. If you're looking at kids who experience this or that kind of event, well, then you need to define what it means to be a kid and put your age ranges on that. Others have made other kinds of limitations, and it's all fine, but you want that list so you can go through the articles and start to exclude the ones that don't meet your criteria. Where you search for the articles is super important because, well, in fact, you can get criticized if you don't search all the possible places that the research could be published or could be available, and therefore you fail to find stuff that should have been in your meta-analysis. We're going to come back to this topic when we talk about bias much later on in the workshop here, because it's a little bit different depending on the resources available at your particular university or wherever you are doing the research from. And then, of course, the importance regarding inclusion or exclusion of the gray literature. So you go ahead and you start doing this search. In the perfect scenario, you would have a complete list of the exclusion criteria before you started searching the literature, but that might become an iterative thing too. Mostly because, well, researchers are really creative people and they have, you know, ideas and do great research and stuff, doing things that you never thought about, right? That's why part of this is so fun. So you had no idea that stuff was out there. And since you didn't know it was out there, you didn't know to put it as an inclusion or exclusion criteria. So this could be a bit of an iterative process. That means some of the searches need to be done more than once. Keep track of your search terms and how many things were found with each of the search terms. Yeah, depending on whether you get lots or tens of thousands, you might have to reevaluate some things. One other thing I'd like to point out while we're here, I mentioned that the electronic databases get updated periodically. They don't just necessarily add in the latest articles from whatever journals are in that database. I mean, yes, they do that. Of course they do that. But they also add in, say, other journals, or let's see here, maybe they didn't have a journal from, I don't know, 1996, and suddenly they get that, so they throw that one in there. One of the reasons you don't want to have to repeat these searches, certainly not months later, is that you could find stuff that you didn't find before, or stuff you had found before somehow isn't there. Anyhow, the results don't necessarily align over time. So you want to be able to say, on this day, I searched these databases using these terms and I found these results, and leave it alone. Okay. Otherwise, things can get really, really tricky. Again, that whole thing about excellent planning, here it is. All right, so we're talking about the results from the databases, and we need to talk about sensitivity and specificity. There's lots of definitions of these terms, but here are the definitions that I like best. Sensitivity is getting all of what you want. I mean, who wouldn't love that? I get everything that I want. What could be better? In meta-analysis, what this really means is that your search results include all of the articles that should be included in your meta-analysis. In other words, nothing is missing. You got all of the stuff that should be there is in your results. Specificity says you get none of what you don't want, which means that your results, when you search these databases, don't include articles that shouldn't be included in your meta-analysis. Now, it should be immediately obvious to everyone that you are not going to search the database and have perfect sensitivity and perfect specificity. That's not going to happen. That's not in the realm of reality. So one of them has to give. And in practice, what most researchers do is we tend to err on the side of sensitivity, meaning we give up on the specificity. We get stuff we don't want to ensure that we didn't miss something that we were supposed to have. The practical side of that says that it means that there is more work for you and your team to do to go through the possible studies to eliminate those studies that are not supposed to be in your meta-analysis. In other words, sacrificing the specificity necessarily increases the workload. Hopefully, it also increases the quality of your meta-analysis because you got more of the articles that you were supposed to have for this particular meta-analysis. But I do admit that the increase in the workload can be substantial and time-consuming. So that sensitivity and specificity. Okay, let's say that you've gone through all of this and you now have the stack of articles or the list of articles that you're supposed to go through. Now you need to determine what part of the article you or some member of your team is going to read in order to determine if the article should be included. Since this could be hundreds or thousands of articles, reading each one is certainly not realistic. Oftentimes I have found that reading just the title, typically not sufficient. You have to at least read the abstract or the method section or whatever else, but you've got to do at least some reading of lots and lots of articles in order to figure out which ones you're supposed to be including. This takes lots of time, lots of effort, and great organizational skills. The last thing you want to do is end up reading the same article a dozen times. It will happen. Okay, been there, done that, that'll happen to you. But you want to minimize the number of times it happens to you. Because of the volume of articles, this is typically done by more than one person. You can see where I'm going with this. Once you've got more than one once you have more than one person reading these articles, you are going to have to do some sort of inter-rater reliability measure to ensure that there's consistency between the two or more people who are doing this reading here. You need to train everybody to whatever standards. This really should be done very early on. And the inter-rater reliability is something that you will have to report. Okay, which is why you want to do it early and you want to do that well, have that number nice and high there. All right. Now you have to figure out what you're going to collect. I argue that before you figure out what you're going to collect, you should stop and figure out which statistical software package you'll be using to analyze your data. The reason being that data organization may differ between the various packages, the various options may differ between the packages, and so you want to make sure that when you're setting up this data set, it is going to be ready for whatever software that you're going to use. Obviously, we're using Stata here. The meta-analysis commands were introduced in Stata 16. I'm presenting in Stata 17. As was noted earlier, Stata 18 is now available. If you're using 16, 17, or 18, everything that I am showing in this workshop will work for you. If you have a prior version of Stata, there were community contributed commands, specifically METAN, M-E-T-A-N, that would do meta-analysis for you. Did a darn right nice job, I gotta say. And there's actually a couple of Stata Press books that pull together all the different articles regarding the user contributed, community contributed commands for that. But we're not going to use those here. We're going to use the built-in Stata commands, and they all start with meta. So we're going to meta set the data. If you're familiar with Stata, you know how you can survey set the data or XT set the data, TS set the data. Okay, this is another one of the sets, and we're going to set it as metadata here. There's a couple of different ways that you could do that. I'm just going to show you one of them. But when you're getting started, if you look at the help file, if you just type help meta, you'll get the help file for this. And what you'll see is that there's at least half a different ways you could organize your data. And you want to be aware of this so that it can inform you as to what you're going to be collecting from your articles. Okay, so you want to know that before you start collecting data. That's critical. I've had folks come to consulting who hadn't looked at this before and kind of cringed when they saw that, like, oh, got to go back and redo stuff. So in the spirit of not having that happen to you, read the help file for whatever you're going to use. Stata is a most excellent place to do a meta-analysis, but there's also R, and then there's also a package by Michael Borenstein. I forget what it's called, but it's something meta-analysis something, and that is also really good. He's got it up to date with all sorts of cool bells and whistles. So any of those three things will get the job done for you. All right. So there's the metaset command. You can use meta esize, which is what we're going to be using today because our data set contains mean, standard deviations, and sample sizes for two groups. The two groups are usually called experimental group and control group, but that doesn't mean that's what they have to be. That's just the way they're referred to. So there's some sort of common terminology. I'm working on one meta-analysis where the experimental group is the number of times kids in foster care speak to their biological mothers in a certain period of time. And then the control group is the number of times they speak to their biological fathers during this specific time. Clearly, it's not experimental control, but it's just one group or the other, and that's just the way they get called. So there's that. Here's some examples of what you might get with the metaset command. So here, all we're talking is the effect size variable and the standard error variable, or you could have the effect size, the lower confidence interval, and the upper confidence interval here. But anyhow, think, and honestly, I put everything into Excel to start out, okay? And this is the way the data set needs to end up. I guarantee you 110% that this isn't the way your data set's going to start out. You are going to start off with an Excel file that looks like a train wreck. And that's okay. Everybody starts there. I promise it's okay. What you're going to do is say, okay, these studies gave me this, these studies gave me that, they gave me this. And what you're going to do is work on getting yourself into the same metric so that at the end, you have a column of effect sizes that are all in the same metric. And it usually doesn't matter what the metric is. It just matters that they're in the same metric. And then some measure of the standard error, whether it's the standard error, whether it's confidence intervals, whatever it may be, that's what you're going for. But it is certainly not the case that you're going to go through all of your studies and they're going to be really nice and give you all the same type of effect size with its standard error. You're going to have to work for that part. And that's okay. That's okay. That's part of the process. In ours, we're going to have the n, the mean, and the standard deviation for one group, and the n, the mean, and the standard deviation for the second group. We'll get to that in a second. Lots of different ways the data can be put in, but you just want to know what you're aiming for when you're collecting the information out of the studies. The social sciences, I usually find the ends, means, and standard deviations, but in the medical fields, maybe you find odds ratios. It doesn't matter. Just get into a common metric here. Data collection is rarely straightforward, okay? Here's the point about the two data sets. Don't worry about it. You will have two data sets. It's all good. The other magic here, the other thing that you really need to keep track of is where you're finding this information within the article. Okay, now I'm older, and so my thought when I started doing this was I would print out the article and highlight, you know, where I found each of the pieces of information that I needed. And my younger colleagues kind of shook their head. No, girl, that's not what you do. And they have it all in PDFs. And I didn't know you could highlight in PDFs, but you can highlight in PDFs. Who knew? And not only that, you can color code that. And they got all fancy with their color codes and PDFs and stuff like that. However it is that you are going to work with your group, that is fine, as long as you are all on the same page and you are all doing the same thing, because it will come time for people to go back and double check your work, and you will be double checking other people's work to make sure that, say, you typed the numbers incorrectly. Okay, we're all human. It's really easy to type 34 when you meant to type 43. It's really easy to misplace a decimal point or overlook a number. So there will be people going back, looking over things, making sure that everything was done accurately. And as long as you were all collecting information and marking the information in the same way, all will be well in the world. Yeah, let's see here. I think I went through all of that. Okay. Another possibility, and we're not going to get to the idea of a meta regression in this workshop, but if you do have designs on doing a meta regression, you might want to try to collect that information as you're going through the article, so you don't have to go through the article so many times. So you'll want to do that. The other reason that you want to collect for multiple variables is that although finding the information for the effect sizes is usually not so difficult, the stuff for the meta regression really could be. And if you find that only like 3 of your studies collected this variable that you thought would be a great predictor in your meta regression, and then it's a non-starter and you got to move on to something else. So anyhow, be thinking in those terms if you're thinking meta regression may be in your future. Yes. Okay. So this slide here says that it is break time. It is 1 hour into our 3-hour session. So this is a good time for a break. It's going to be a short break. It's only going to be like about 5 minutes. So if you could come back at 5 minutes after the hour, that would be lovely. If you have any questions, comments, or anything else, I'm going to be here during the break, and you're welcome to unmute yourself and ask me questions. Okay? All right. See you back in 5 minutes. All righty. Going to get started again. I didn't have any questions when we started the break. Do you have any questions now that you've had a moment to think about things? Okay, then let's talk about some missing data. All right, there's 2 types of missing data in a meta-analysis. There are missing studies and there are missing values. So when you think about missing studies, it's kind of like unit non-response in survey data. Survey data is my other real big passion, so I make connections where I can there. You don't want missing studies, right? The missing studies usually lead to some sort of bias, and that's all bad news. So you don't want any of that. The second type of missing is due to missing values from a particular study. So this is kind of like item non-response, or a respondent not answering all the questions on your instrument. Let's start with the missing values from your articles. Because how you handle these different kinds of missing data are very different than most other types of research. The cost of missing data, item missing in meta-analysis, is often very high because there's no way to get more data. In other words, if you've already included all of the studies in the literature that are relevant to your meta-analysis, it's not like there's more studies you can go out there and get. Okay, if you're working with human or even non-human respondents, if some of those humans weren't terribly cooperative, like human beings can be, and they don't answer all the items on your instrument, you might be able to go find some other humans who will answer all your questions, and you're good to go. In a meta-analysis, you don't typically have that luxury. So what is available to you? There, of course, is the traditional kind of form of imputation. Usually people think multiple imputation, although there's some new cool stuff in Bayesian that I'd like to dabble with. But before you get to any of that stuff, you can try to find an acceptable method to replace the missing value using information that is currently available to you. And one of the very best places that I found was in this manual for this ES program written by the late Will Shadish. And Will and I were friends. I really do miss him because he was a sweet guy, gentle soul, and a meticulous researcher. I mean, just the highest quality research. And he wrote this program, ES for effect size, and then this amazing manual. And I just found out like last week that the link to it off of the UC Merced website, because he was founding faculty actually at UC Merced, that link is no longer working, and I haven't found a replacement link yet. But I did bash around a little bit and found it kind of on some other sites, so you can look around for it. But what he does is he goes through not only the formulas for the different kinds of effect sizes, but he goes through what happens if you need to substitute one thing for another and the consequences of this substitution for unknown information. So let's talk about a little bit of this here. So let's assume that we've got our continuous data situation. We're collecting n's, means, and standard deviations. You find the n, mean, and standard deviation for both the experimental and the control group, and if you're lucky, you've got a total of 6 values. However, one of the article only gives you 5 values, and the n for one of the groups is missing. Now, you might be able to figure out what that n was supposed to be if you knew the total number of subjects and the number of subjects in the experimental group. You can obviously just do the subtraction. If you can't do that, what you might be able to do is just substitute the n that you observe in the experimental group for the n in the control group. That doesn't actually compromise the calculation of the effect size very much. So that's pretty okay there. If you had all but the standard deviation for one group, you might assume that the standard deviations for the 2 groups were equal. It's a little bit more of a compromise than assuming that the n's are equal, but it's not too bad. However, you should be really reluctant to assume that the means of the 2 groups were the same, right? So when you're thinking about these numbers that you have and what might be missing, substituting one number for another in some situations like n is not all that problematic. And in other situations, if you don't have both means, well, that's kind of a non-starter. So the brilliance of what Will did was he went through all of these different scenarios and talked about, you know, well, how much of a compromise is it? How good or how bad is that? And so that's something that you would want to consider before you go to other options here. You can actually do reasonably well if all you have is, say, the F statistic, the degrees of freedom, and the p-value. You can actually get the effect size out of all of that. If you can only find the p-value, you can still get back to an effect size. You need a little more information, but yeah, you can still do that. But you do need to have the exact p-value, okay? So some of this works better for the more recent articles than some of the, say, the older articles. You know, back when I was trained, dinosaurs were roaming the earth and we didn't all have desktop computers. And so we would just report whether the p-value was above or below 0.05, but we didn't actually have an exact p-value because we were actually looking things up in the back of a stats textbook. Right. And so if that's all you have, then this estimation of an effect size from a p-value isn't going to work. You actually need to have the exact p-value. What are you going to do about missing studies? What you are really worried about are high quality research studies that found non-significant results. Okay. Because that, of course, you start thinking in terms of publication bias or something like that, or possibly small study bias here. That's a tough one. Okay. Don't have any real, surefire way to address that question, because how you go about it will be different in your different research situations. But that's where you really need to focus your attention and your efforts. High quality research that didn't have statistically significant results, because it's still true that it's difficult to get non-significant results published. That's kind of what the issue is there. Okay, let's see here. You can also try to contact the authors of the study with the missing data and ask for the value that's missing, or values. I've had to do this before. Okay, I had to do this more than once. Some authors were very understanding and took the time to provide the requested values. There were others who simply ignored us. That was unfortunate. We had one very kind researcher respond and said that she would be more than happy to provide us the missing value, which was a mean, so we really needed it. But the data were stored on tapes like they used to use on mainframes, and that the tape was no longer readable because it was mostly disintegrated in a closet behind her desk. So sometimes that older data come back to get you. But keep in mind when you're doing your meta-analysis that you may need to reach out and contact people. And as you publish articles, people may reach out and contact you. And I take this as an opportunity when I'm asked to provide such information to be very kind to the people who are requesting the information, because I know what it's like to be on the receiving end of those emails. So just kind of think ahead to your future self and always be kind here. And when you're publishing, don't forget your descriptive statistics. Make life easy for some future researcher who's going to come along and use your study in a meta-analysis. Get your descriptives in there, get your, all that good information so someone else can come along and do the meta-analysis. Let's see here. What are your options for missing studies? You can try to contact researchers and ask if they have non-published papers. You can search for master's theses or dissertations. You can talk to people at academic conferences. That actually comes up more than you might think. I go to the joint statistical meetings whenever I can, and I have heard that conversation a goodly number of times. I've also seen people post inquiries on relevant mailing lists, which I thought was an interesting way to go about it, but I hope it's effective. I think that should be. Again, you need to be careful here because we don't want to include low quality research. And sometimes the reason the research wasn't published is because it was low quality, not necessarily that it didn't find statistically significant results. It's just that, something went wrong, or, hey, we didn't know about this. Hey, this happened in the middle of the study, whatever. And it's not, publish worthy. So maybe, it shouldn't be in your meta-analysis, but that's stuff you need to think about, okay? All right, we need to talk about different types of effect sizes, and there's lots of them. There's actually books that talk about the different kinds of effect sizes. It's super cool. Some of them are for continuous outcome variables, other are for binary outcome variables. If you look at the Stata blog, Stata's got its own blog page, and if you look back, I forget how far back it is now, but they talk about R&D effect sizes, the R class and the D class effect sizes. Super cool, easy to read, very interesting. Have a peek at that when you can. The D class effect sizes are usually calculated from the mean and standard deviation. and they are a scale difference between the means of the two groups. Okay, so that's what it is. What do I mean by scale? It means it got divided by something. All right. If it got divided by the standard deviation of the control group, we call it Glass's delta. If it got divided by the pooled standard deviation, pooled between the experimental and control groups, we call it Cohen's d. If we had Cohen's d and we did a little correction here because Cohen's d tends to overestimate the effect sizes in small samples, then we call it Hedges g. Okay, so there, again, variations on a theme here. In my example, I'm going with a Hedges g. In general, the advice, at least currently today, is to use Hedges g because the correction to the effect sizes is very minimal and is usually never harmful. So in any ways, everyone's familiar with Cohen's d and they understand how it gets calculated, which I think is a huge benefit. But when you go to do the meta, you might want to consider Hedges g here. Let's see here, R class, we're not going to talk about this too much, but they're a ratio of variance attributable to an effect divided by the total effect. So in other words, a proportion of variance explained, and examples of this type include eta squared and omega squared and good stuff like that. So I did mention that when you go to collect your data, you are not going to find that everybody was kind enough to give you effect sizes in the same metric. Okay, that, I don't know, has never happened for me. I kind of don't think it would ever happen, but if it did, you'd be really lucky. For all the rest of the times, you need some sort of calculator that will convert from one effect size metric into another. All right, so there's lots of them online. I put my favorite one there. I particularly, I use that one all the time. I like that, but there's lots out there. Before you go converting the effect sizes though, stop and think for a moment, okay? Let us assume that some of your effect sizes were in a continuous metric. So you had ends, means, and standard deviations, and other effect sizes were in the metric of odds ratios. You need to put them all in the same metric. Which way should you go? Should you go with the continuous measure and convert the odds ratios into something like a Hedges g? Or should you, in fact, turn your Hedges g into an odds ratio? Which way should you go with that? Anybody want to unmute and answer that? Without reading the next slide first. Oh, come on, be brave. Somebody talk to me. Which way should you go? All right, if nobody wants to talk to me, my feelings won't be hurt. No. All right. The answer is you should probably take your Cohen's d into an odds ratio, but not the other way around. Why would that be true? Because you can imagine taking a continuous variable and making it binary. So binary, you'd get an odds ratio, right? But what would it be that you had a binary variable and in some way was able to make it continuous? That, you know, you can't really get your head around that. I don't know how that would work. If I've got a binary variable, I don't have any good way to get it back into some sort of continuous metric, right? So when you're working with these calculators, they'll go which way you ask them to go. But it's up to you as the analyst to bring your common sense to the table and say, does this actually make sense in the real world? I've got a couple references here. regarding fourfold tables. Those are with all the odds ratios and stuff like this. The other thing to keep in mind, it really becomes quite an issue here, is rounding error, because, you know, the effect gets rounded before it gets put into the original publication, and then maybe you round it or the calculator rounds it, and all that rounding error eventually adds up. So just try to keep an eye on that and not round if you can help it. We've already discussed the fact that an effect size is an estimate, and because of that, we need some form of standard error, confidence interval, something to give us an idea of how accurately that estimate is estimated. The software should actually give you that, you know, when you're using statistical software and you ask for an effect size. I think everything I've seen in the last several years gives you not only the effect size, but its standard error or confidence interval, whatever. It can be problematic if an article reports the effect size, but not its standard error, because that would be really tough to estimate. And so that's probably a place where you'd have to contact authors or something like that. Now, despite the large number of effect sizes that are available, there's still some situations where there's no really agreed upon way to measure the effect. And up until just recently, I would have said my two examples are count models and multi-level models. But some members of our group have been working on some recent stuff for getting effect sizes for multi-level models, at least for continuous outcomes, okay? Not to speak of anything. Although if you've got a multi-level logistic, you're still in the metric of odds ratios, and that's an effect size, so you're good to go there. But like other areas of statistics, this is always evolving and getting better and better. And so hopefully we'll have more effect sizes to play with sometime soon in the future. All right, let's assume for a second that we've got a data set and we're going to get ready to start doing something. You want to check to make sure that everything looks good, just as the same as you would with any other data set. What you're really looking for are effect sizes or something that might look kind of crazy. If you're in the metric of a Cohen's d, you know, you would see anything 0 or greater. But if you see a Cohen's d of like 150, you need to go back and figure out why that is, okay? I mean, theoretically it's possible, but it's very unlikely. So you're looking for stuff like that. How you do that depends on the size of the data. I have never been lucky enough to work with a big enough data set where I couldn't just look at the data set and visually tell if there was a problem. But I have read about meta-analyses that had like hundreds of studies in there, and then you'd probably use some sort of graphical method or something like that. But personally, I haven't been that lucky yet. Let's see here. I don't like tests of outliers and stuff because that definition to me is always a little bit questionable. And I had one situation where we did use a test for outliers. And when we took out the outlier that was identified and reran the test, it found another one that was an outlier. And it just, you know, every time we did it, we had exactly the same problem. But in addition, we couldn't figure out why these studies were considered to be outliers. You know, there was nothing seriously obvious about the study that would make it be an outlier. And since we had no compelling reason to exclude the studies, we ended up not excluding anything, although we did do a sensitivity analysis and say, you know, without this study, you know, which was identified as an outlier using this test, you know, we get this, which is very similar. So you that. Anyhow, I would be kind of careful about that. We will go over outlierness and ways of looking at it. Stata's got a new option that's totally super cool that you can use to look at this. But part of the reason I totally faked the data was to put in a really obvious outlier so we could have a look at something like that. Let's see here. I think I already covered this. So here's the question you should be asking me: where are we ever going to get to the data analysis? And the answer is yes, we'll get there soon, but we have to talk about some other things. And if you feel like it has taken us forever to get to the analysis, get used to that feeling, because when you run a meta-analysis, 95% of your time is going to be collecting and cleaning the data. The analysis part is usually kind of anticlimactic. You'll be done with the analysis in like half an hour or something. And, after all of these months and months of collecting data, and like, oh, the analysis is done in half an hour. Oh, man, you're hoping for a little more fun. But let's move on to weighting. Okay. The issue of weighting in a meta-analysis comes from the fact that some studies have more subjects or respondents than other studies. And in general, when N goes up, the sampling variability goes down, hence the hence the estimate of the effect size is more precise. So really what's going to happen in the meta-analysis is that the more precise estimates, the ones with the smaller standard errors, tend to get upweighted, and the studies with the larger standard errors around their effect sizes, they tend to get downweighted. This is called inverse variance weighting. In Stata, you might know it as analytic weighting. These weights are relative weights, and they will sum to 100. Okay, you don't need to calculate any of this yourself. The software is going to do it. The weights will be shown in the output. All is well in the world. All right, any questions before we dive into the hairy, scary topic of heterogeneity? Okay. Heterogeneity is a huge topic in the area of meta-analysis. And you need to handle this very carefully. You have to report various measures of heterogeneity in your output. And this is one thing you do not want to screw up. I can't emphasize that point enough. Go get yourself an excellent reference book. I've got references at the end of this. Get a reference book and follow it to the letter with respect to reporting this stuff. Do not screw this part up. Up until now, we've focused on finding these effect sizes, and although we've considered that there's variability around them, we're now going to really focus on that because at least according to Michael Bornstein, who's one of the kind of big names in meta-analysis, that's really what we've come here to do, is to talk about the variability between these studies. And that's where the real action is. So that's why this is important. This variability is actually comprised of two components. There's the variation in the true effect sizes, which is called heterogeneity. I wish they had called it something else, but they call it heterogeneity. And then there's the spurious variability, which is just random error, sampling error, whatever you want to call it. So there's the variation in the true effect sizes, and then there's just random error. We just need to pull that apart. So the purpose here is to get this measure of heterogeneity, and that's what we're going to go for. The heterogeneity minus the spurious variability, okay? That's what we're going for. We're going to discuss a couple of measures of this. I adapted much of what is coming up here from Introduction to Meta-Analysis by Bornstein, Hedges, like Larry Hedges of Hedges G, that Hedges, Higgins, and Rothstein. Edition 1 came out in 2009. The second edition came out in 2021. I cannot stress how helpful and highly recommended reading this chapter is. Okay, if you don't have this book, borrow it from a library. It's worth buying. However it is, get a hold of this. This is good stuff here. All right. We are not going to go through the part where we're going to go through all the different calculations for this, but I am going to go through some definitions. Okay. So if the heterogeneity was in fact 0, that would actually mean that the all of the studies in your meta-analysis shared the same true effect size. All right. But of course, they wouldn't all be the same number because there's that spurious stuff, that sampling error stuff. And so that's going to mean that the numbers aren't exactly the same. Instead, your effect sizes that you observe are going to fall within this particular range around this true effect size. So here, there's only one reason that your effect sizes vary, and that's your random error or your sampling error, whatever you want to call it. This idea is associated with common effect and fixed effects models, and we're going to discuss those a little bit later. But you need to keep in mind that the only thing that's moving around in these kinds of models is your sampling error. Okay. Now let's take a different scenario here, and we're going to suppose that the true effect size does vary between studies. Okay. In this scenario, now we've got two reasons: the heterogeneity, okay, which is the true effect sizes themselves are different, and we still have our within study sampling error. Now we need to separate that heterogeneity from the within study sampling error. This idea is associated with your random effects model. Again, we'll be discussing this later. Without looking at the next slide, anybody want to guess why the true effect sizes could vary between studies? Why would that be true? Somebody be brave, unmute yourself, talk to me. Okay. All right. Here's some of the reasons. In Stata, in the Stata documentation, they talk about clinical heterogeneity, and this is the variability in the intervention strategies, the outcomes, the study participants, and then they talk about heterogeneity that comes from methodological issues such as the study design and conduct. So imagine, for example, that you're taking a college class and the professor for the class says, look, everybody is going to go out and do a meta-analysis, and here, or you're going to, excuse me, you're not going to do the meta-analysis, you're going to do the primary study, and everybody is going to answer this research question. You're going to use this methodology. You're going to use these measures, you know, with whatever measuring device, whatever it is, an instrument, whatever, and you are going to use this sample of undergraduate students. If you went out and did this, we would be kind of thinking in terms of the scenario in which you have only one true effect, right? And the only difference that's going to show up in your effect sizes is going to be this random or sampling variation. If, on the other hand, the assignment was everybody was supposed to go out and conduct a study on this broad question, and that's all you're given, then you're more likely to see differences in, quote, true effect sizes, because you're all going to be answering slightly different questions with slightly different instruments and slightly different methodologies and thus and so. And so that's how you can kind of think about these two scenarios here. There's 3 steps necessary to separate this heterogeneity between the true effect sizes. So when you have multiple true effect sizes, that heterogeneity from the within study sampling error. You're going to start off by computing the total amount of study to study variation that is actually observed. Secondly, you're going to estimate how much of the observed effects would be expected to vary from each other if the true effect was actually the same in all the studies. And then third, you're going to assume that the excess variation reflects real differences in the effect sizes. In other words, heterogeneity. Okay, that's what you're going to do. The next series of slides I have go through these different measures of heterogeneity, and they kind of build on each other. You start with Q, and then you realize, hey, there's some issues with Q. Let's improve on this. We go on and we move on to these other things here. And we're going to skip a whole bunch of slides so that hopefully we end kind of on time. And we're going to skip all the way down here to my summary slides. Okay, so Q is one of the measures of heterogeneity. It is a ratio of the observed variation to within steady error. It's talking about the heterogeneity of the true effect sizes. It's referred to in the Stata output as a test of homogeneity, but it's a sum rather than a mean, and that means it's very sensitive to the number of studies in a meta-analysis. Well, for a measure of heterogeneity, I don't like that. You know, I was really good with those first 3 bullet points, but you lost me there when you say, wait a minute, it's sensitive to the number of studies. So we get to tau squared. This is the variance of the true effect sizes, but it's a theoretical value. So we calculate, I have it as t squared, and in the literature, they bounce around whether they call it t or tau, because this is basically lowercase and this is basically uppercase of tau. So sometimes you see this referred to as tau squared, but it's just uppercase tau squared. However you want to call this, it is the estimated value of this theoretical value that, of course, we could not calculate. It is Q, but with the dependence of the number of studies removed. Okay, so I like that. And it answers the question of how much do the true effect sizes vary. Okay, I kind of like that. So I'm feeling good here. Now we have I squared. Be most super careful with I squared because lots of people misinterpret this. So be so careful here. I squared is the proportion of observed variance that is heterogeneity as opposed to random or sampling error. It's a proportion. You can think of it as a signal to noise ratio, all right? It is a descriptive statistic, and that's important to realize because it means that it does not actually estimate any underlying quantity, all right? It's just a signal to noise ratio. That's all it is. It is a measure of inconsistency across the studies, and Borenstein would argue that this is why you came and did your meta-analysis, is that you wanted to know about this inconsistency across these studies that are looking at the same research question using very similar methodologies, similar instruments, similar everything else, and you're looking at this inconsistency across these studies. It is not a measure of the real variation in the underlying true effects because it's a signal to noise ratio. That's what it is. Okay, people get really worked up about I squared. Be careful with this. The other thing that you use this for is when you're thinking, is there enough of what we're going to call the excess variability or heterogeneity here to warrant, say, a meta-regression or a subgroup analysis or any of those other things that we're not going to get to in this workshop, but you're usually looking at I squared to tell you if that's something that you get to do. And then there's H squared. H squared is the ratio of the variance of the estimated overall effect size from a random effects meta-analysis to that same quantity from a fixed effects meta-analysis. And we have not gone over random and fixed effects meta-analyses, but we're going to in the next slide. So we are almost there, but that's what H squared is. And included in here because you do see it in the Stata output. All right, so before we start talking about the different types of models, any questions? Okay. Okay, it's a lot of stuff. All right. As of version 17, Stata offers 3 types of meta-analysis models. They are the common effect, fixed effects, and random effects models. Let's go through each of these in turn. Your common effect model assumes that there is one true effect size and that each study equals this true effect size. Each study effect size is equal to this true effect size, but there is still the random error. In practice, this is a very, very strong assumption and would very often be violated, okay? I don't actually think I've ever seen a common effect meta-analysis published, okay? That's a super strong assumption, but this does exist, and you need to know that it exists because other things are variations on this theme. Okay, your fixed effects meta-analysis assumes that the observed study effects are different, but they're fixed, okay? All of the studies of interest are assumed to be included in the meta-analysis. Ouch, that is a super strong assumption, and you can imagine how easily that would be violated, okay? So again, you want to know what the assumptions are underlying these models, because you're going to choose between a common effect, a fixed effects, or a random effects models based on the assumptions the model makes. That's the determining factor, not anything about your data, but how reasonable are these assumptions. All right, our fixed effects models are appropriate if all of the studies included in the meta-analysis are identical in all important aspects. I tend to work in the social sciences, and I have to say that's an assumption that I've never seen met in the social sciences. Maybe more plausible in some of the medical fields, but even then, I'm not sure about that part. The purpose of the meta-analysis is to compute the effect size for a given population, but not to generalize the results to other populations. This goes back to that very strong assumption that all of the studies that are supposed to be included in your meta have been included in your meta. Okay. I personally choke on both of these assumptions here, and so I stay away from a fixed effects model because I can't believe that either of the assumptions are true in the meta that I work on. The calculations that are used in the common effect model and the fixed effects models are actually the same, but as you notice, the assumptions between the two models are different. Okay, so again, we need to think very carefully about the assumptions that are being made and choose the model based on which set of assumptions seem to be the most reasonable given our data set. Okay, so a random effects model assumes that the observed studies are different and random. The studies included in the meta-analysis are a random and representative sample of the population of studies of interest. I can live with this. Okay, this one, I can live with both parts of this, okay? I can really go for the idea that the effects are different. Okay, I guess they're random, but I can go for they're different because I don't see that many replication studies in the social sciences. I wish I saw a lot more than I do, but I don't. And so I'm going to go with this idea that their study effects are in fact different. And I would never know if all the studies are that were supposed to be included are. I only have access to the databases that are available through the University of California system. I could have missed something out of the gray literature. Maybe my time span wasn't correct. Maybe my language thing is coming to bite me. And the fact that there's nobody on my team who can read another language has meant that we're not including some of the studies that really should have been included. I don't know these things, but I'm going to go with, I got a random and a representative sample. That's the closest set of assumptions to the data sets that I see in my research. So I'm going to go with that one. you would use a random effects model because the research studies were conducted by independent researchers. So I don't see any compelling reason to think that the studies are functionally equivalent. It might not make sense to assume that there's a common effect size because the data are gathered from different subjects using different interventions, different measures, different all sorts of other things. And so that common effect size idea doesn't work for me there. And given the differences between these studies, you might want to generalize your results to a range of similar but not exactly identical situations or scenarios. So a random effects model is the only type of model where you get to generalize your results beyond what you have. And so again, things to think about here. Because of these assumptions, the random effects meta-analysis is often recommended and is what I most frequently see in the literature. Stata actually offers many different estimation procedures for these types of models here. We're only going to look at the ones for the random effects model. I'm actually going to have to skip that because I'm running out of time. So it's in my notes, but I got to skip over that. Sorry. It's important to note, though, that the calculation of that weight is different for each type of model. So just keep that in mind. Okay. Running the meta-analysis, guess what? We are finally up to the point of reading in data. Okay, 3 cheers for reading in data. All right, before we get to this, any questions? Okay. So I have an Excel file. I took a picture of my Excel file, and my Excel file looks like this. So T is for treatment, C is for control. I have N, mean and standard deviation for my treatment, and N, mean and standard deviation for my control group. Here are my studies. I totally faked all of this, and you can tell that I totally faked all of that. But that's what my cleaned up data set looks like. This isn't my initial train wreck data set. This is my cleaned up all good to go data set. We're going to use the import Excel command to read this into Stata, and then we're going to use the meta esize command to declare that the data are meta-analysis data. I'm going to use some options here. The esize hedges G option is going to tell Stata to use hedges G instead of Cohen's D. The random option is used. We're going to discuss this. Well, we've already discussed why we're using the random there. And then we're going to use the study label option so that when the meta-analysis run, the information is in the output. So looking here at column A here, I want this information, the author and the year, to show up in either the table or the graph of my meta-analysis. And so I have that in here like this. However, this column is organized and displayed, that's what it's going to look like in your output. So make it look however you want it to look like. That's the way I like it. You know, you do whatever you want to do. It's all good. We're going to run these commands and voila, imagine I have got Stata 17 open. Like I said, I haven't gotten Stata 18 yet, but I'm waiting eagerly. Let's read in our data here. Let's rock and roll. Okay, there we go. Let me move that over so you can see we've read in some data. Super cute. If I wanted to click on browse, I could do that. Let's see here. It's not so interesting right now. Yeah, it just looks like the Excel file. So there's nothing interesting here yet, but let's run this command here. Our command is meta esize. We are presenting these variables. The order of the variables is critical. Do not rearrange the variables. Stata is expecting the variables in this order. So you will put those 6 variables in that order, or you will get very interesting results in a kind of unfortunate sort of way. E size, we're using Hedges G. I want this as random. And this here is the variable author, which is that string variable that I had right there. Let's run that. Okay, Stata gives us a little bit of output. Look at this. Don't just blow past it. Actually look at this and make sure that everything makes sense to you. You want to make sure that the right number of studies is in there. You got this. Here's your, and you'll see what happened over here. Stata put in a whole bunch of new variables. We can click on browse again. And this is much more interesting here, right? Because now we've got much more interesting stuff. They put in this variable. All the Stata variables start with an underscore meta, so that you know that that's something Stata added. But this is the stuff that Stata is going to be doing its magic with. Okay, so my effect size is Hedges G. We've got the label here, the variable name, all the rest of this stuff here. I'm going to use random effects in REML. I'll be talking about that stuff a little bit later, but that's where it is here. The default is REML, so I don't need to put that there, but let's run the command and see what we get. All right, so finally, data analysis output. We're feeling good here. Always look up here at your summary, make sure that things are the way that you are expecting them to be. That the number of studies is the number that you're expecting it to be. Here's our tau squared, our I squared, and our H squared.
Christine, could you make the font larger? Thank you.
Okay. I appreciate having the font larger. The only downside is that now you don't see the whole thing in one shot. Okay. As far as I squared is since it's a percent, you can tell that say 1% is low, and as you might think, 97% is kind of high. All right, so let's just kind of think about that for a second. Here's our H squared. Remember the ratio between the random effects and the fixed effects analysis here. Here are our studies. This is that author column, okay? And that's why I said that I wanted it to look like this so that in my output, I could see who the author is and the publication date. You don't have to have the publication date. You can have this any way you want, but that's the way I like it, so that's the way I did it. This is the Hedges G value that was calculated from the ends, means, and standard deviations for my two groups. So Stata did that math for me and also calculated the confidence interval. And then here is this weight variable that we talked about. If you added this all up, it would come to 100. That's why it says percent here. It would add up to 100. In this example, all the studies are more or less evenly weighted, but I've worked on a number of projects where there's a couple of studies that have these huge weights and other studies have very, very small weights. And that's something that you may need to investigate regarding, sensitivity and stuff like that. But this is your weight variable here. This theta down here, this 1.260, this is kind of your overall effect size here. It's a weighted average of these things, weighted by this, right? So here is our theta here and its confidence interval. If you want to know if theta equals 0, well, we're going to say no, it doesn't here. Here's your test of homogeneity. Remember, I said Q was called a test of homogeneity here. And obviously, this is statistically significant. So we reject the idea of homogeneity. We say there's heterogeneity, which is extremely consistent with these values up here. So that's what you get when you do this. Most folks, however, want this. Make that a little bit bigger. Okay, there we go. This is called a forest plot. And as you see, it contains all the information that was in my output from the summarize, but we got some extra stuff. Some people like having the raw data here, other people do not. So you take it or leave it, however you like it. Here is your effect size with its confidence interval here. And we got a little scale down here. And then this green, call it a diamond thingy, tells us where this overall effect size is with its confidence interval as well. You can see that the higher the weight, the smaller the confidence interval here. So this has got a fairly small or large weight, small confidence interval. These have even larger weights, and look, you can't even see them here. This has a relatively lower weight, and you see that there's bars here. So that's the correspondence between this. And then of course you get your tau squared, your I squared, your H squared, and your tests of Q and theta down here. And then Stata reminds you that this is a random effects Rummel model here. I did not have much time in this presentation to put in most of the great options that are available, but I did throw this one in here. If we do this, it looks exactly like the last one, but this null ref line here puts a reference line at 0. And you may wish to do this, at least in this example, it really brings home the fact that all of my studies have effects that are greater than 0, although some of them starting to get a little bit closer to 0 here. But if you've got stuff that goes back and forth around 0, having this ref line here may make that a little more obvious for your viewers. So let me go back to this. All right, now we get to skip a whole bunch of slides because the output took up a whole bunch of slides. So let's see here. Okay, we discussed all of this. We discussed this. We discussed this. Okay, awesome sauce. Let's see, we discussed all this. So looking at my output though, or whatever you want to look at here, you can see though that this con study here, this con 2016, has a very large effect size compared to everybody else. Not necessarily a crazy high weight because some of these other things are very well estimated, but this is a very high effect size. And you may ask yourself, does that cause a problem? So a Galbraith plot can be helpful here. Let me come back to here, and run that. So if, what?
I think there was an I missing.
Oh, no, but a typo in there. Oh, yes, I do have an I missing. Thank you. There we go. There we go. All right, got to spell things correctly. All right, so here you get this kind of plot here. On our y-axis, we have our standardized hedges G. Okay, notice it goes from 0 up to 40 here. And along the x-axis here, we have precision. So precision is low over here and high over here. This green line here is no study effect. So this is 0. If the effect size was 0 or close to 0, it would be, you'd see all your data hovering around this 0. But we don't see that. We see this regression line here with these studies here. Now, we happen to know that this is the Kahn study because I already told you he's my outlier that I put in there. But if you didn't happen to know that, you could use this M label option with the author option, and we would do that, and we get this, and then we could see now this all writes over one another, right? But when you're looking for outliers, that's not a problem because the outlier is by definition out by itself. And so now you know which of your studies to go looking at to see as this is a possible outlier. So my first order of business when I see an outlier like this is to think in terms of a sensitivity analysis as opposed to some sort of outlier test. So I'm going to think, okay, sensitivity analysis. Stata gives you a couple different ways to do it. I'm going to show you 2 of them. One of them is to do exactly what you would think, and that is just to leave the study out. Okay, and you can do either the summarize or the forest plot, whichever you like. The original one had been, let's see here, what was it? 1.26, and this is 1.123. So boy, I don't see that really is all that different. And you see that we're down 1 here. This came down from 97 and change to 91. Not a huge drop. I mean, it's a little drop and stuff, but not enough to really write home about. I skipped a break, but we're running out of time. Sorry, folks, we skipped a break. We're into sensitivity analysis. Yeah, we ran that. Here's the forest plot, the same thing, leaving it out. Here's our summary here. The overall effect size drops from 1.26 to 1.12. Both values are different from 0. Each of the measures of heterogeneity will decrease, although I squared doesn't decrease by all that much here. And so what I take from this is that even though that Hedges G value is very large, this study doesn't unduly influence my results. And so I'm going to say that he's not a problem. If you want to do this another way, you can use the leave one out option. This here can be used either on meta summarize or meta forest plot. And what it does is it runs the meta-analysis as many times as there are studies in the whole data set. And then each row is the result if you had left this one out here. And so what I'm seeing here is all of these things look very, very consistent. You know, if something was a really crazy cuckoo outlier, you see this is a little bit different than the rest of them, but not bad. But if something was a real crazy outlier, then one of these would look very different from the rest. And that's just not what I am seeing here. Okay, so again, I'm going to say that although I tried to put in an outlier, he turned out not to be so much of an outlier. Any questions? Okay, let's compare the 3 types of models. Although the assumptions for these models, common effect and fixed effects models, may be strong and often violated in practice, we're still going to try and run each of these to see how our results would differ. And then I've got a table that shows you the output. So what it looks like, oh, here's my leave one out stuff here. I just ran those commands there. So with common, with fixed, and then with random. And then I came over here and summarized all of that output there. All right, so let's have a look to see what happens here. The effect sizes and confidence intervals are the same across the three models, but the weights and the measure of heterogeneity are different, right? And that makes sense to us because the effect size and confidence intervals aren't calculated as part of a model. That's based on the data that we gave to Stata. So what Stata calculated was the weights and these measures of heterogeneity, and those differ between those three models. In the common effect model, there are no measures of heterogeneity because, again, remember, we assumed that that did not exist. So, of course, there's no measure of that. In your fixed effects models, there's no measure of tau squared. The value of I squared is similar in the fixed effects and random effects models, but the value of H squared is quite different given the way H squared is defined. We're not surprised there. The value of theta is the same in the common effect and fixed effects models, 1.351, but it's different in our random effects models. One of the things, so when you're thinking about good references, I said Introduction to Meta-Analysis by Bornstein et al. Michael Bornstein also wrote a book called Common Mistakes and Meta-Analysis and How to Avoid Them. That's really worth having. That is really worth having because you don't want to make some of the mistakes that he describes in here. And the book is actually kind of cool because it's like there's 2 pages on this is the mistake, here's the details, here's why whatever the mistake is wrong or why it's not true. And it just goes through thing after thing after thing that he has heard throughout his career. And one of the places where he spends an awful lot of time, besides the misinterpretations of I squared, is the misunderstanding of when you're supposed to use the fixed effects and the random effects meta-analysis here. And so I would be very careful here. Again, that decision should be based on the assumptions that are most reasonable given your data, not on the results that you get. All right. Let's see here. Estimation methods for random effects models. Stata currently offers 6 of these. I took very heavily from the Stata documentation because where else was I going to get this kind of information here? I'm going to go through this terribly quickly so we can get on to other stuff here. Restricted maximum likelihood, and empirical Bayes assume that the distribution of your random effects is normal, but the other 3 estimators do not make distributional assumptions about your random effects. Your Remmel method produces an unbiased, non-negative estimate of tau squared and is commonly used in practice. It's the default method in Stata because it performs well in most scenarios. And I will say that, at least in my experience, the random effects with a Remmel estimator is what I see published most often. Now, I admit I don't read a huge variety of literatures because, I just don't have that kind of time. But in the social sciences, that is what I am seeing mostly. Here's some other information regarding the other estimators. You're welcome to read through this and this slide here. But what I did then, and you can see in my do file, is I went through and I ran this using all the different estimates. This no meta show just gets rid of the header information here. And I summarized all of this here. So here is the different methods that are available. We have tau squared, I squared, and H squared. And except for like here, all of this looks fairly consistent, and it's a little bit higher here. Again, this is a little bit higher. This is higher, and then this one here. So the idea here, though, is that these things will impact how your measures of heterogeneity are calculated, what they come out to be. You choose a method based on your data and what assumptions are most reasonable. The Stata documentation is very well written on this. It's readable. Yes, there's some math in there, but it's totally readable. Here, I put in the weights for each of the studies for each of the different types of estimators. And you can see that for all the estimators, the weights are approximately, I don't know, I think they're all fairly consistent. Okay. That is that discussion of estimators. Any questions, please? Before we move on to potential sources of bias, any questions at all? Okay. Hey, I'm feeling kind of lonely here. All right. So as we've talked about, it's really important to include all of the relevant studies in a meta-analysis, but some of them may be unobtainable, and this could lead to some sort of bias. All right. Publication bias used to be the big thing that everybody talked about, and that has really changed in recent years. And so just keep in mind that when you're writing up your meta-analysis, you may need to, mention that you looked for this, but this should not be the only thing you talk about, or, that's not going to go so well with the reviewer. The idea of publication bias is that at least for academic journals, they prefer to publish studies that report statistically significant results rather than studies that report statistically non-significant results. Okay, and that's the idea behind this. The idea is that these studies, for some reason or another, have a larger effect size. And so, or a more precisely estimated effect size. And precision, as we have discussed, tends to move with N, so this might be a larger study. And so the smaller studies with the less precisely estimated effect size might not get published. Also, if the effects, there's two things going on here, and don't confuse them. That's part of why this discussion has changed, is you don't know why the study didn't get published. I mean, yes, there's always quality issues, but it could be that the N was low and the effect size was not precisely estimated, or it could be that the effect size was just small. Okay, and those two don't necessarily have to go together. So there are two things that could be at work here: the fact that the effect size is small, and or it was not well estimated. Kind of along the same line, researchers may be loath to write up a paper that reports statistically non-significant results, believing that the paper is more likely to be rejected. I can't tell you how many papers I've been on where this has been kind of the final call by the first author, that, we don't have enough here to write about to publish it. And so it gets, put off to the side in favor of other things. This happens. I know this happens. You've done lots of analyses for such papers. So that's a real concern. So this effect on the meta-analysis is that you have missing data. In other words, there's rows missing from your meta-analysis data set because that study that should have been in your meta-analysis wasn't published. It's not available anywhere, and therefore it's not in your meta-analysis. So this, of course, could lead to biased estimates of your summary effect, especially if the reason that there wasn't a statistically significant result is because that the effect size was estimated to be small. Yeah, so for any given sample size, it's more likely the result to be statistically significant if the effect size is larger and larger. So the problem is those studies that estimate a small effect size. Okay, let's see here. What else do we have here? Okay, I think we went over all of that. Other potential sources of bias. So we've discussed some of this language bias. There's a bias that the English language databases and journals are more likely to be searched. And that's true not only in the United States. Honestly, that's true in a lot of countries where English is not the language of the country, but that just happens. So we need to be aware of that. The availability bias means that you're including those studies that are easiest for you to find or to access. So to which journals or databases does your university subscribe? So I've encountered this one. I was working with a group of folks from various universities on the African continent, and they just didn't have access to a whole bunch of the electronic databases. They only had access to a few of them. And that was a major concern for them. And they finally got some help from some folks in Europe, and, everything ended up okay. But you have this problem even here in the United States. If you're working at a small private college, you probably don't have free access to all of the different electronic databases that, say, someone who works for the University of California has. So that availability bias is a real thing. It's related to this cost bias thing, because if you're at a place that, for example, doesn't have access to all of these electronic databases, you might have to pay for access to them. And since researchers always have very limited funds, the idea is that you can only pay to access some, not all of them that you would wish to. And so, again, there's a bit of a bias here. Familiarity talks about including studies from one's own research field. And this is where I found it to be advantageous to have an interdisciplinary team. It always surprises me what these other folks come up with and what they know about and all these other resources. I have learned so much from being on interdisciplinary teams. I can't recommend it enough. But we all have familiarity bias. That's just because we're human beings. And so different points of view and different perspectives, really the way to go here. Duplication bias here. Multiple similar studies reporting statistically significant results are more likely to get published. You can do some checking of reference sections for the different articles to see, if you can't find other articles that way. But when you do that, you will find that you get a lot of duplicates because, everybody's referencing the same articles here. And then there's the citation bias. So studies with statistically significant results are more likely to be cited and hence easier to find. So anyhow, those are some of the things we do need to, there's another one coming up here. So a funnel plot is a good way to start looking for potential bias. So I'll get you a funnel plot in just a second, but it does kind of look just like a funnel with a line down the middle. And ideally, the dots, which each dot represents a study in your meta-analysis data set, will be approximately symmetrical around the mean of your effect size. Okay, so you want kind of a symmetrical even distribution of studies above and below that line that represents the mean of your effect size. That's what you're hoping for. But if that's not what you see, there might be some sort of bias because the studies with certain effect sizes, usually the smaller effect sizes, are missing. What you're worried about are the holes in there. And I'll show you one in just a second. It's used to be referred to publication bias, but we're not using that term here because the studies could be missing for a variety of reasons. And so we need to be careful there. Here's the graph here. Okay, this is the funnel plot of our example data set. Here is our average estimated effect size, and each of these dots represents a study. Here's our 2016 study out here. But if you look at this, you say, well, gee, I wish there was something up here, and I kind of wish there was something down here. You know, I've got some data over here, and I don't have any corresponding data over here. And this is what really gets me, because these are the larger standard errors right here. But strangely, this is with the larger effect sizes. Usually I see the missing stuff over here on the smaller effect sizes here. Let's see here, what else did oh, this only goes over what I already said. So I ran the meta funnel plot / contours command here. I ran this command here and I got this graph here. And I thought, that has got to be the screwiest thing I have ever seen. What gives? So let's talk about this and then I'll show you how to fix this up. And I put this in here because I figure I'm not the only person who's going to have this problem. And I want you to see how it is that you can kind of make sense out of something that looks this cuckoo. Okay, so here's our red line, and this is the estimated effect size here. The blue dots are our studies. This is Con 2016 out here. So we're good with that part. We see that part from up here. But notice what I said. Our red line is here at our estimated effect size, and our red line is still here at our effective. But what's this goofiness over here? What's this thing? So what I asked for was for contours at 1%, 5%, and 10%. So think p values here. So 0.01, 0.05, and 0.1 here. And so that's what these contours represent here. But they're nowhere near my thing because this got centered at 0, not over here. And that's why I was saying previously, remember, I said put in that null reference line and showing that all of my studies don't get near 0. They're away from 0. And so this here didn't help me the way that it would otherwise be helpful. So anyhow, I looked at this and I said, this is just disturbing. I don't like this. And I contacted Stata technical support, and the wonderful folks there said, stop panicking, girl, do this instead. And they sent me this code. And I thank them quite dearly for sending me this code. And I don't need to go through all the whys and wherefores here, but they just quietly do the meta summarize so that they can get theta. They put some options into a local here, and then they run my command, add a plot on top of it, and we get this. And so we put our pseudo 95% over here. I don't really get my contours the way that I had hoped for, but at least I got this stuff moved over here, so it made a little more sense. So anyhow, the contour enhanced funnel plots are a new favorite among people doing meta-analyses, because you can get these contours that correspond with your p-values, except for if your data are really weird like mine. And like I said, I just faked my data, but I have to imagine this would happen to somebody. So here's the solution. Don't freak out here. And then I have a little note as to why this was a problem and what we did about it. But the idea for the funnel plots here, let's just go back to this, is that you don't want to see these gaps here. And we need to go talk about these gaps in my data here. And we're going to do that in just a minute after we talk about small study effects. Stern and some friends here coined the term small study effects to describe the phenomenon that smaller published studies tend to have larger effect sizes. Why would it be that if you're a smaller effect and you're published, if you have a small n and you're published, the effect is larger? Why is that? Well, as we said before, it's the relationship between n power and effect size. Right, we're holding alpha constant. And so if I have a smaller n and I had a statistically significant result, I had to have a larger effect size. They were very, very careful to point out that there's no way to know why this would be true. So there's other things that could be at play here. It could be publication bias. It could be that the smaller studies, especially if they're the first studies done in an area of research, maybe included subjects who were more ill, more motivated, more something than the later conducted studies that included more subjects. It's also possible that these smaller studies had better quality control. I can see that. I remember when I was doing primary research, the smaller studies, we had much better control than, once we got lots of people on the project and lots of people running subjects. And, I can really see where that would be true. In the end, though, any one or some combination of these reasons, other reasons may explain why the smaller studies reported larger effect sizes, but this is an important thing to remember when writing up your results. Okay, so we got to go back to our idea of missing points in our funnel plot here. There were a couple of things proposed in the literature, one by Begg in '94 and one by, I don't know if it's pronounced Eager or I guess it's Eager. I don't know how to say his name, sorry, in 1997. However, both of them suffer from several limitations. The tests and even the funnel plot itself may yield very different results simply by changing the metric of the effect size. That does not make me feel good. Okay, I don't want it to be true that if I change the metric of my effect size, my finding that there could be bias in here suddenly appears or disappears, because whether there's bias or not shouldn't depend on the metric of effect size that I'm using. Those two things aren't supposed to be related, and yet they are with these tests. Both a reasonable number of studies must be included in the analysis, and those studies themselves must have a reasonable amount of dispersion. So I don't, again, really like stuff that's tied to N, but can't really get away from that. These tests are often underpowered, and therefore, just because you get a non-significant result doesn't necessarily mean that there's no bias. That part, please keep squarely in mind. It will tell you if there is bias, but the converse isn't true. You can't claim that there's no bias if you get a statistically non-significant result with either of these. So let's look at this. You can use meta bias command. There are 4 options on this command: Begg, Egger, I hope it's pronounced Egger, Harbord, or Peters. Harbord and Peters are only used with binary data, so we're not going to go over those. So the command looks like this. This is a non-parametric rank-based method here. And here is our p-value here. If you use the other option here, this is a regression-based measure here. Again, not statistically significant. So I don't have any evidence that I do have a publication bias or some sort of bias problem, but I can't rule it out. Okay, and keep that in mind as we go through the end of this. Now, how do you address some of this? Rosenthal came up with what he called a fail-safe, and I liked the logic of this. This isn't implemented in Stata, but it's discussed in the Bornstein book. But it's a very interesting logic, and then people worked on this, improved it over time, and then there is something that's implemented in Stata we'll get to in a couple of slides. So for just a second, let's go over this. In the output from your meta-analysis, we see the summary effect and a p-value, which indicates if the effect is statistically significant from 0. Okay, we got that. In the presence of bias, the summary effect would be larger than it really should be, assuming that the small studies are missing, the studies with the smaller effect sizes are missing. So we have overestimated our effect. If the missing studies were included in the analysis, so we got rid of the bias, the summary effect might no longer be statistically significant because it's going to be smaller and closer to 0, therefore it might not be statistically significant. The idea here was to calculate how many studies would need to be added to your meta-analysis in order to render your summary effect non-significant. So think about that for a second. If I add studies to my meta-analysis with smaller effect sizes, how many do I have to add so that my summary effect is no longer statistically significant? Well, if we only had to add a few studies, we would be really worried, right? If we're only missing a couple of studies and all of a sudden our estimated effect is really close to 0, now I am really uncomfortable. Something's terribly wrong. However, if I have to add a lot of studies to make the summary effect non-significant, now I'm not so worried about the possible bias because it seems unlikely that I missed a lot of studies. I might have missed a few, but I didn't miss a lot of them. So that's the idea here. How many do you have to add to move your estimated effect back towards 0? Of course, there's some drawbacks to this. First of all, it focuses on statistical significance rather than practical or real world significance. And as we know, there's usually quite a distance between the two of those things. It assumes that the mean of the missing effect sizes is 0, but the mean actually could be negative or slightly positive. And if it was negative, fewer studies would be needed to render our summary effect non-significant, right? That makes sense. And on a more technical note, this whole thing was based on a methodology that was acceptable when he proposed that measure, but it isn't considered acceptable today. But that's the idea. And I just want to get you that idea so that we can see what comes next. Orwin comes along and modifies this Rosenthal fail-safe N to address those first two limitations. Orwin's fail-safe N now allows researchers to specify the lowest summary effect size that would still be meaningful, and it allows researchers to specify the mean effect size of the missing studies. Okay, well, that sounds good. What's implemented in Stata is a trim and fill method. So what do I mean by trim and fill? Duvall and Tweedy proposed this method. It's an iterative procedure that tries to estimate what the summary effect size would be if in fact there was no bias. So think of our funnel plot, okay? It shows bias. There are gaps in places, and so we know that we suspect some studies are missing. And typically they are on, let's see here, on the lower right. Actually, they're missing from the lower left. So to estimate our new summary effect, the procedure trims the most extreme studies from the lower right and recalculates the summary effect size, okay? And this is all done behind the scenes. Don't worry, you don't lose data from your real data set. Okay, in theory, once all of the extreme effect sizes have been trimmed, an unbiased effect could be calculated. However, as we've been stressing, when you calculate an effect size, you've got to calculate the variance around it, right? Now, when trying to calculate the standard error around this new summary effect, this trimming has caused a substantial decrease in our variance, right? We cut n down and now we're in trouble. All right, so to account for this, the studies that were trimmed are added back, a process called filling, so that a more reasonable standard error can be calculated. So let's be clear that the trimming process is used only in the calculation of your new unbiased summary effect size, while the filling process is used only in the calculation of the standard error around that new, hopefully unbiased effect size. So the advantages to this approach is that it gives an estimate of the unbiased effect size, and there's usually a graph associated with this, okay? And it includes all the imputed studies, and it looks very nice. The disadvantages include a very strong assumption about why the studies are missing in the first place, excuse me, and that only one or two aberrant studies can have substantial influence on the results. All right. So we can use the meta trim fill command here. There's a funnel option if you would like a graph here. I'm going to run both the commands here in just a second. So let's do that. Here's our meta trim fill. Oh, I guess it shouldn't say funnel here because this is the actual trim fill here. So this is the non-parametric trim and fill analysis. We got this. So we started with our 17 studies, we imputed 5, and that's where that N of 22. Here is our observed. Here is our imputed plus observed. Notice this is higher than this. Why is it higher? Because when we were looking at our funnel plot, let's look back here at our funnel plot, the studies were missing from over here, which is a higher these would have a higher effect size than our average. So when we fill over here, we're moving the effect size larger. That doesn't always happen, so don't expect that to be the common output. And then here you can also look at the funnel plot. I thank Stata for doing the Bruin blue and gold for us here for the default colors. I don't think they did that on purpose, but it was nice. And you see here are our 5 imputed studies, these gold points here. Notice that they are all well above our average or our estimated effect size. And that's why this is up here at almost 1.5. So that's what this is saying here. It is usually obvious if bias is a problem, but it's not nearly as obvious as what you're supposed to do about it, other than to discuss it in the limitation section of your paper. It should always show up there. Whether or not there's anything from either the tests or the graphs that indicate that there's a potential source of bias, you do need to always discuss that. And always remember that most tests for bias are underpowered. So that's why you can't say, oh, you know what, they were all statistically non-significant, I'm good to go. They're underpowered. So I would be cautious there. All right, I do have a little more time, so I can go over cumulative meta-analysis if people would like that. But before I get there, does anybody have any questions? Is anybody brave enough to unmute themselves and ask a question?
I have a question, Christine.
Yes.
Is there any one preferred over the other as far as big or eager for the bias testing?
No, I don't believe there's any real reason to prefer one over the other. I always do both and report both.
Thank you.
Mm-hmm. Any other questions? Okay, then let's take a very quick tour of cumulative meta-analysis. Okay, this is fun. It's an iterative process in which the meta-analysis run first with only the first study, and then again with the first and second study, and then a third time with only the first, second, and third study, and so forth and so on. And the same thing is true for the creation of your funnel plot. So the first line in your table of output there shows the summary effect based only on the first study. The second line shows the summary effect for only the first two studies, and so forth and so on. Of course, the final summary effect will be the same as from the regular meta-analysis, because by the time you get down there, all of the studies are used in the cumulative, and of course for the regular one. But the studies can be sorted in different ways to address different questions. All right. So the way I typically see this done, and it's not the only way, but the way I've typically seen it done is to order the studies by date. And you can kind of ask yourself, well, when did we really come to a conclusion on this kind of question? And so I've seen this more in medicine or in public health than I have in the social sciences, but you can order the studies in different ways, and that ordering matters. Okay. So if you only want to look at the largest studies, you can certainly sort based on N. If you want to sort by year, that's kind of what I'm used to. Whoops. That was supposed to be there. Let's try that. It's important to know if surgical technique increases life expectancy, so lots of studies are done, and at what point in time do we have enough studies to kind of answer our question. So those are some ideas here. You can use it as a method to detect publication bias, but only if you've got lots of studies in this. And for this, you would sort the studies from most to least precise. And you can look at the forest plot to see if there's a shift and the magnitude of the shift, not just if there's a shift, but a magnitude too. So we can use meta summarize, cumulative for this. I'm still going to use my random option. If there's a, you want to sort by something here, you can put that in parentheses here. In my example, I used publication date. But let's go back to my data. If we go back here to my example data here, notice I don't have a column that's just publication date. Notice all I have is my authors with the dates. So really what I want to do here is pull off these dates and dump them off into another column. That's really what I want to do. Now notice this is necessarily a string variable because I've got a bunch of letters and commas and stuff in here. So I want to pull this off into its own variable and then make it numeric. That's what I want to do. How am I going to do that? Got a little bit of data management. I've got the code here, but I also have it in my do file. Let me come down here. Looks like this. So I don't know if you're familiar with it, but Stata's got this handy command called split. And I love the split command. It is so terribly useful when working with string variables. And it basically says, split my variable up, right, into multiple variables. In this case, I'm using the variable author, which remember is my string variable that contains this information. And P is for parse. And what am I going to parse on? The default is space. So I can parse on this but I put it as comma space there just to make it clear. And when I do that, let's rock and roll that, I get two variables called author1 and author2. I don't care about author, but look at this. Hello, I got my dates all in their own little column. I'm going to rename it to date, and then I'm going to destring it. This is still a string variable. I want a numeric, so I go ahead and I do that. Now I can do my meta summarize with my cumulative thing done by my dates. And so we see we're in date order here. It puts the date order over here. This is still because the study label is still in effect here. We have all of this. So this is the effect size for just this one study. This is the effect size for study 1 and study 2 together, study 1, 2, and 3 together, study 4, 1, 2, 3, 4. And then this number, of course, looks familiar to us because now all the studies have been used by the time we got here. Now, because my effect sizes are so similar to one another, you don't see a really huge difference there. Let's run, go ahead and run that. Right. And you can get reference lines in here and do whatever you want to do here. But what tends to happen over time is you start to see these dots kind of get into a line, and you start to see the confidence interval shrink and shrink and shrink as you're adding more and more information here. And then that's what it will look like for that. Let's see here, got that. All right, so that's my very, very brief thing on cumulative meta-analysis. Some concluding remarks, and I promise we're rushing to the end here, and we're going to make it. The purpose of today was only to introduce you to the what, why, and how of meta-analysis. I understand that I spent a lot of time talking about how you collect the data, and I did that in part because in my work as a statistical consultant, I have seen so many times when people have come to me asking, well, how do I run a meta-analysis on my data? And I have to have the very difficult, uncomfortable conversation saying, well, you didn't quite collect your data correctly. And, you know, I never wish to say that to anybody and say, you got to go back and do this. And so I don't want you to have to go back and redo things. So I'm trying to, you know, make clear what it is you're trying to do so that you'll have to reread the studies many times, no matter what you do, but maybe we can minimize that and kind of make the process a little bit easier. You definitely want to know what you need to report as you go through each of these steps. And so that's why I spent the time on the guidelines telling you, okay, you got to report this, you have to have this flow chart, you have to have this, you have to have that, so that when you go through and actually do these steps, you're writing down all these numbers and you can make your flow chart easy peasy and move forward from there. Let's see here. You definitely want to think about effect sizes. If you're doing primary research, you know, include the descriptives and the effect sizes and their standard errors in your publication. That's becoming more and more of a requirement than it used to be. So keep that in mind. Definitely, you know, once you've done your power analysis, you've done your primary research, go see how accurate you were. Okay, sometimes you were spot on, other times not so much. It's all a learning process. It's all good. Make sure to include the standard error of the effect size, include descriptives. Let's see here. two final points here. Always be nice when people ask for additional information, because at some point that's going to be you asking for additional information. I try very hard to make sure that older data, syntax, commands, files, script files, whatever, are readable with the current technology. Yes, I still have zip disks. My son finds this to be absolutely hysterical. You know, they're big, they're chunky things, they're kind of heavy. He finds it to be completely hilarious. Okay, but finding the zip drive isn't difficult, but finding the drivers for your computer a little more challenging. My point is, try to keep your files up to date so that you can go back and do your own meta-analysis on your own research, if that's going to be a thing or something. But keeping your data in some current readable format is always a worthy endeavor. We didn't discuss lots of the topics that we could have, including multiple imputation, multi-level modeling, psychometric meta-analysis, network meta-analysis, SEM. Oh my gosh, there's just so much stuff here. Lots of great stuff that can be taken beyond this here. But those advanced topics are beyond the scope of the workshop. I mean, I just did the introduction, the bare bones introduction, and still been carrying on for 3 hours here. The area of meta-analysis is an area of statistics that is evolving and changing rapidly. Witness the new additions to Stata 18 and lots of other good stuff yet to come. So review your guidelines on a regular basis before you start any new meta-analysis, and make sure you are up to date. All right. I think that is everything that I had. I've got references. Here are my references here. So you can go through those.